Hi everyone, welcome to the video series on vectorization and embedding. In the previous couple of videos, we talked about the difference between vectorization and embedding. Today, we will focus on hashing vectorizer in this video. Uh, we, all, we already have talked about the bag of words, the count vectorizer, TF-IDF, and what are the pluses and minuses, the advantages and disadvantages of count vectorizer and TF-IDF. We also saw how TF-IDF or count vectorizer are not suitable or not capable enough to be used for online machine learning model. And we'll see how hashing vectorizer can be a solution for online models. Let's first talk about what is hashing vectorizer, how does it work, and then I'll show you the same text classification example using IMDB dataset. Okay, so hashing vectorizer, this is well suited for cases where we have streaming data and we are consuming the streaming data into a machine learning model, for example. Let's see how it actually works. So it is memory efficient compared to the count vectorizer and TF-IDF vectorizer. These traditional vectorizers, they store the vocabulary in the memory. In contrary, um, in hashing vectorizer, this is not the case. And we will see how and why that is not the case. With traditional methods like count vectorizer and TF-IDF vectorizer, you're going to need a lot of memory to store the vocabulary in the memory. So in contrast to the traditional method, um, there is a huge memory savings with hashing vectorizer. Now, with the hashing vectorizer, since it is stateless, that means it doesn't remember the state. It is particularly useful for online modeling, let's say online machine learning model. You don't need to retrain or adjust the vectorizer when the new data comes in. This is very, very important and a key point with hashing vectorizer. Some other aspects, you can achieve parallelizability with the hashing vectorizer because this is stateless. So what is the meaning of stateless? We'll talk about it when we discuss how the hashing vectorizers are trained. The fixed output size is also similar. I mean, in TF-IDF and count vectorizer also we have the fixed output size. The difference is the output size in TF-IDF is dependent on the size of the corpus that you're using to train the vectorizer. Here is not so. It is regardless of the size of the corpus. It's up to us. So when we configure the hashing vectorizer, we mention the dimension of the vector or vocabulary. So in that sense, it is different compared to the traditional TF-IDF and count vectorizer. Since it is stateless, hashing vectorizer tends to be or proves to be, I mean, a lot quicker and faster. There is no need to build a vocabulary, and hence there is no need to, tune the vocabulary length as such. With hashing vectorizer, this is not required as the vector size is the same. If you have mentioned that your hashing vectorizer should be able to handle 50,000 words, that's going to be the same. Now, the basic concept of hashing vectorizer is the input is your token, and there is a hash function which takes the input data and applies the hash function on the input data. The resultant output would be some integer value. Now, depending on the input tokens or the word, there would be different integer values being computed. And we use these integer values much like the same as we do in TF-IDF and the count vectorizer. We use the output of a hash function, which is an integer value, and we use the integer value as index, which is what we have seen in the TF-IDF and the count vectorizer. The first step in the hashing vectorizer is we tokenize. Now, this tokenization can be any of the tokenizer that you can pick and choose. For this example or illustration, we will make an assumption that tokenization is by word, and we'll look at how each of the word is fed to the hashing function, and the hashing function generates an integer which is similar to the index of the feature or the word, like in TF-IDF and the count vectorizer. Step number 3 is to form the vector for the input document. Now you have two different variation, as in count vectorizer. Here also one representation can be binary representation. That means the hash value is set to 1. Does not matter how many times the token is present in the document. It will be simply set to 1. If it is not present, then it is going to be 0, which is same as count vectorizer. The other one is a frequency-based representation. That means if the word is appearing 5 times in the document, then that would be represented by 5. And every time the word reappears or appears in a new document, the hash value is going to be incremented by 1. So let's take an example here. This is the text, and the hash function applied on apple gives you the output of 2. Hash function applied on banana gives you an output of 0, and on orange it gives you an output of 3. So let's make an assumption that the feature vector size is 5. That means we are saying um, I can have uh, 5 buckets or 5 places. That's what it means when we say the number of features is 5. So the vector initially will be random, initially not known, so it would be a 0. So for this particular input document, the vector would be something like, question mark, question mark, question mark, or it could be 0, 0, 0, or could be null, null, null. Now, after the transformation, as I mentioned earlier, so there you could go for binary representation, or you could go with frequency-based representation. When you talk about the binary representation, the apple hashes to the index 2. So they set the position 2 to 1. So basically this position is set to 1 here. Banana hashes to index 0 here. So set the position 0 to 1, and you see this is being set to 1 here. Orange is the index 3. That means the hash function output of orange is 3. So now for 3, we're going to set that to 1, and rest of them would be 0 here. So this is a binary representation. That means if the apple, let's say the apple is appearing twice, it doesn't matter. We're not going to make the apple, which is index of position of 2, is not going to be 2. It's just mentioned as 1. So likewise, now let's talk about the frequency-based representation. The first occurrence, apple, position of 2. Okay, so this is a position of 2. We will make it 1. Then banana, which is a position of 0. So that is also 1 here. Again, apple comes, and that is position of 2. Same word. So position of 2 again. So we need to increment it by 1. So that becomes 2. And likewise, the orange is going to be 1 because that appears only once in the input document. The last one is a 0. So you notice here I mentioned the number of features is 5, so that means the vector size is 5 here. The last one is 0 because nothing maps to that particular position. So it's pretty much similar to what we did in count vectorizer and TF-IDF, although the method is different. Now, along with this hash function, you also get a sign as an output. So when you apply the hash function on a token, it returns two things essentially. So it returns the hash value. So let's say the number of features that you have given is 500 or 5,000. The hash value can be anything like 499. And then along with this, you're going to get a sign which is positive or negative. So that means it could be something like this 499. Now, this 499 does not literally mean negative 499. It doesn't mean the index is still the same. So in your vector, the position number 499 would be set to, let's say, -1 because the sign is 1. Next time the same word comes, it will be -2. Again, the same word comes -3, and so on and so forth. This has nothing to do with real negative value in the sense that the index remains the absolute value. Negative and positive is just the way to increment or decrement here. The sign preservation ensures the token, when hashed, can be assigned a positive and negative index value. So this is done to have more information about the token. It does not mean the index itself is negative. It rather means the value at that index is either incremented when you have positive sign or decremented when you have a negative hash. If the sign is positive, then the value in the hash index is incremented. If the value or if the sign is negative, then the value at the hashed index is reduced or decremented. So some of the drawbacks of hashing function, as you notice here, two words can result. Let's say you have word 1 and this is my hash function and you apply word 1 and let's say word 2, they can result in the same output 499. This could happen. So that's why, in order to avoid the collision, what we do is the number of features that we actually assign it to a very large value, let's say 100,000. So, that's the way to avoid collisions. Now, different words might be hashed to the same index, and that means it's very difficult to distinguish those words in terms of the vector representation. Now, with the mechanism that we have here, the words are mapped to an index, and you could have same index for more than one word. It's difficult to do inverse mapping as well. So you cannot, by looking at the index, there's no way you can interpret what's the original token here. So these are the drawbacks of the hashing mechanism. Some more shortcomings here, since it is stateless, that means it does not maintain the global information like we have in TF-IDF. You have a vocabulary. Count vectorizer also maintains a vocabulary. Number of features is mentioned at the time of creating the hash vector. So if you mention that to, let's say, 50,000, that cannot be changed only way to change would be to retrain the hashing vectorizer with a new value of number of features. This is another shortcoming here. No handling of out of vocabulary words. In typical vectorizer out of vocabulary words, the word which is not seen during the training can be ignored when you want to transform the new data. With hashing, every word actually gets a hash value even if it is not present in the training. This behavior has both pluses and minuses. Sign preservation, which is additional information about the token, this can also be both advantageous and also can create problem. While the option to use the signed hashes, it gives you more information about the token. It can introduce the negative values in the vector. That means the vector orientation might change. So that might not be suitable for all types of machine learning algorithm. So what it means is, let's say the hashing vector gives you the vector like 1, 2, 0, 0, -5, -2, 0, 1. And these minus values can be problem with some of the machine learning. In the previous demos, I was using multinomial naive Bayes. This particular machine learning model does not accept the negative values. So in the demo that I'll be showing here using hashing vectorizer, I'll show you how multinomial naive Bayes cannot work with these negative values. So this is again a drawback. So that means we have to choose a particular machine learning model or suitable machine learning model which can work with hash vectorization method. So when to apply hashing vectorizer? When you have a large data sets is very useful to consider hashing vectorizer because count and TF-IDF being memory intensive and also one of the reason is you cannot build online machine learning models with count vectorizer and TF-IDF vectorizer. Now, hashing vectorizer does not store any vocabulary, so it is memory efficient. It can also handle streaming data. That means the new data comes to the hashing vectorizer, even if it is not seen in the training time, it's perfectly okay. So this is an excellent choice to build a online machine learning model. So that was your conceptual understanding of a hashing vectorizer. In the demo, I'll be picking the same dataset, IMDB movie reviews dataset for text classification, and I'll be showing you a Python demo where I'll be using the hashing vectorizer. So this is your movie sentiment analysis, the same IMDB dataset. In place of TF-IDF, I'm using hashing function and vectors, multinomial naive Bayes. We'll see if it's not going to work with hash vectors, so we'll have to use something else. And I think in my code, I'm using stochastic gradient descent model. And then we will evaluate as usual. Data set is here. I'll be attaching the data set and the code in the description below. Here is pandas. I'm not going to run it because some of the steps can take really long. So that's the data set here. And as usual, we'll focus on the cleaned text column, which is in the end. This column I got after pre-processing of the raw data. Now, X and Y, and then we will divide the data into two parts. The first part I'll be using for training. That means I'll use this data for training. This one I'll use it for partial training or incremental training, corresponding labels here. All right, so So X and Y and train test split just for evaluation. Hashing vectorizer has a number of features as a parameter. Typically, it is set to a very high value, 2 to the power 20, that is more than sufficient to avoid any collision. But the drawback with such high number of features is again the length of the vector will be very huge, and you could also get the problem of sparsity here. So this parameter needs to be properly configured after you know due diligence and experimentations. And the other option is you can do lower casing and in tokenizer stop word like you did in the count and TF-IDF vectorizer. So hashing vectorizer function is part of your feature extraction and number of features. For example, here I'm taking 50,000. That means the length of the vector is going to be 50,000. And notice here I'm transforming the training samples, and there is no fit method. We are not using any fit method here. Why we are not using any fit method here? Because we don't need to. It is hash function which takes the input like a token and gives you an integer value. So it doesn't make sense to really do any kind of training. So we don't need to fit the data to the vectorizer, simply transform. So all your tokens and you get the corresponding integer values for each of the token. So this is how your vectors will look like, and we're going to transform the testing data as well. 20,000 samples in the training, 5,000 samples in the test. And this multinomial naive you cannot use with the hashing vectorizer because the vectorizer has some values in negative, and those negative values are not okay with multinomial naive. So I'm going to use the stochastic gradient descent classifier and mention the loss function. You have variety of choices here. You can go for log, you can go for Huber loss, or you can go for L1, L2, those kind of losses. Huber is a like a balance between L1 and L2. Choose that and train the classifier and then evaluate here. Now here the accuracy is not so good with 0.78. And now the incremental training with the second set, movie reviews 2. Notice I am here again generating the vector for the new set, no fitting required. Simply use the vectorizer, which is a hashing vectorizer, provide the new set of data, and you get a new set of vectors. With the new set of vectors, you train the stochastic gradient descent classifier, because that classifier provides you a partial method to incrementally train the model. That works perfectly fine, and the model is trained. You can use the model um, seamlessly. So this method is very good for situations where you don't want to dismantle or you don't want to completely retrain your model. So this combination of hashing vectorizer with stochastic gradient descent works for situations where you want to build the model to be available 24 by 7. So that's pretty much it here. I hope you liked the information here. And in the next, we'll talk about one more vectorization method. So that was the demo on hashing vectorizer. And with this, we have completed the topics of count vectorizer, TF-IDF vectorizer, and hashing vectorizer. We also discussed the pluses and minuses of each of these vectorizer. In the next video, we'll talk about one more vectorization technique, which is BM25. Thank you all. Thanks for your cooperation and time. We'll see you in the next lecture.